Gabriel Auvinet-Guichard will tell you something about Mexico City. Please go on.
Thank you. Thank you for this invitation to participate in this meeting. I'm Gabriel Auvinet. I'm a professor at the National University of Mexico. I've been involved in this kind of program for more than 50 years. And I will speak about the evaluation and mitigation of soil subsidence in Mexico City. Well, Mexico City is a very large city with a population of 22 million. That's more than the whole country of Netherlands. And it's located in a valley which used to be a lake, a very large lake that was dried in the 18th century. So the city was built mainly on a clay formation, about 200 meters thick, resting on volcanic materials. Everything in Mexico is volcanic. And where you can see a profile down to the limestone that I found at the sea level at more than 2,000, I would say yes, 2,000 meters deep. Mexico City is at an elevation of 2,200 meters above sea level. Okay, as a reference, we have this topographical work, magnificent, made by Diaz Covarrubias that was in 1862 in Mexico City. At this time, Mexico was at war with France, but some scientists, Mexican scientists, thought that some things were more important than the war, and they made this beautiful work on geodesic and topographic condition in Mexico City. So that's our reference for the calculation of subsidence. No, nothing happened. Okay. Well, the subsidence was observed first in 1922 by this engineer, Roberto Gayol, who was in charge of the drainage of Mexico City, and he was accused of that his systems was not working. And he was a very good engineer. He made very accurate topographical measurements. And he said, no, my drainage work is working. What is happening, the city is sinking. So in 1922, there was the first evidence that the city was sinking. And it was until 1948 when Nabor Carrillo, a pupil of Casagrande in Harvard University, showed that the settlement that was attributed to the weight of the buildings was, as a matter of fact, a consequence of deep pumping in the aquifer below Mexico City. So the changes in the piezometric distribution within the soil. And this is the evaluation of the subsidence in the downtown area of Mexico City. The vertical scale is in meters. So we see that starting at the beginning of the 20th century, the settlement presented a slow rate and then it decreased. And we can see this break. It was, at one point, it was decided to no longer install wells in the downtown area. So that was the consequence of this break we can see. But anyway, the subsidence is going on, and in some point within Mexico City area, it has reached more than 15 meters since 1862, that is our reference. And of course, this has an impact of many things in Mexico. For example, the drainage system was a gravity system that, due to the subsidence, no longer worked because the slope of the canals changed, and it was necessary to excavate deep tunnels to ensure the drainage of the city. The last tunnel was built recently. It was finished in 2019 with the participation of some people from here, from Holland. or Netherlands. And it's a 64-kilometer long tunnel with a diameter of 7 meters. And the consequences of the subsidence is, for a civil engineer, is very important. For example, we have a tunnel that has been squeezed by the consolidation or compaction, as geologists sometimes say, of the clay layers. That is, you need a double lining system to ensure that the tunnel will support the deformation induced by the consolidation of the clay layers. Other evidences are these casings, old wells with the metallic casing that are protruding from the soil. Of course, the soil is going down, the casing is not moving, but it's very spectacular to see this evolution in the downtown area in Mexico City. We have also some construction like this monument. It was built in 1910, and initially it was as seen on the left-hand side of the slide, and now it is protruding more than 3 meters from the surrounding ground. That's an Independence column, very famous among geotechnical engineers. And many buildings also built on point-bearing piles are presenting protruding sometimes of several meters. This is an example. It is the main building of the airport terminal, T2. You can see on the left the position not so long ago, almost 4 years ago. And then sometime later, it is always a difference of several tenths of centimeters. There is also a curious phenomenon in the unloaded area, for example, subway lines or like this underpass structure. We have an unloading of the soil, so the soil becomes over-consolidated and no longer presents subsidence. So it's protruding from the soil without piles, only due to the difference between the consolidation conditions below the structure and outside of the structure. During the earthquake of September 2017, it was observed, very large cracks were observed. And they were attributed to the earthquake, but no, these cracks, we know them very well. They are due to the subsidence, the differential settlement at the contact with the perimeter of the valley. We have differences, and these cracks are very important. They affect millions of people in the south area of Mexico City. Many constructions have been demolished, and some solutions have been found, but anyway, it's a very large problem. You can see that these cracks are noticed especially around what we call Santa Catarina Ranch. It's a small mountain at the south of Mexico City, and we see that the cracks appears in the transition between the lake zone and the volcanic structures of the Santa Catarina Ranch. It's on a flange of about 3 kilometers wide. We have cracks everywhere. Okay, how do we measure subsidence? Well, there is an optical survey that has been performed for many years, about 3,000 benchmarks, but we also use remote sensing like LiDAR with very good results regarding relative movements, but not so regarding the absolute movement. With absolute movement, we have an uncertainty of more than 1 meter with LiDAR. We use also INSAR with also some limitation. For example, in flooded area, we can't use INSAR. And this has some problem of interpretation also of the INSAR measurement. But we are trying to use all the available techniques to have a better assessment of the settlement. So we have been able to obtain a map of settlement. We can, in red, we see the settlement with largest magnitude. That will be about close to 40 centimeters per year. Yeah, I was, in the previous presentation, I saw millimeters per year. No, in Mexico, it's centimeter per year, 40 centimeter per year in this red area. Yeah, we can see here. Close to the airport and in the south part of the city. Of course, remote sensing is much more attractive than topographical survey, because instead of obtaining data every 500 meters, we obtain a continuous profile. But the absolute value is not very reliable with LiDAR and INSAR. Anyway, we can obtain profiles from for the subsidence, for example, here from 1862 to 2010 in the Texcoco area, in the east part of Mexico City. Okay. So we have this map that's very useful for engineers. We are supposed to design foundations in this area. And this map has been updated recently in 2022. And we still have the same trend of 40 centimeters as a maximum in the red area. Of course, we have also a measurement of pore pressure. We have about 100 stations in the cities. That's not enough. We would like to have much more stations, but anyway, we are able to obtain the evolution of the pore pressure. We make also measurement. We are not only interested in the surface subsidence, we are interested in the contribution of the different strata to this settlement, because it's important to assess, for example, negative skin friction on piles in foundations. So we use magnetic extensometers to have an assessment of the contribution of the different layers to the general subsidence. And we have some example, for example, a Metropolitan Cathedral. We were able to follow the contribution of different strata during about 20 years. And we can see that the strata, deep strata, deeper than 100 meters, contribute as much as 50% to the general settlement. Okay. If we want to know where we are going, then we can make some simple calculation using soil mechanics techniques, and we can see that in average, we can expect 6 meters per century in the city, with very large difference depending on the thickness of the clay. And in the area where the clay is thickest, it's about 70 meters, we can expect a total settlement of 35 meters. So we are now at 15 meters. We can expect up to 35 meters. And that will not be all, because when the soil will be, when the pore pressure will be completely abated, then we'll have a new phenomenon known as contraction due to drying of the clay. It has already started, and that will take us to the contraction limit. Okay? To mitigate this problem, there is a different strategy, but now we are using deep wells. Instead of wells located, for example, at 250 meters deep, we use very deep well at 800 or 1200 meters deep, and that has an effect to diminish the abatement of pore pressure in the clay formation, superficial clay formation, and we try to keep the soil in an over-consolidation condition in the clay layers, and that ensures that the displacement are much smaller. We also have planned to inject water in pervious layers within the clay, and okay, this strategy is described in much more detailed way in this publication. If you're interested, we can provide you this publication. Thank you very much.
Thank you. Thank you very much. It's real nice. Maybe an unknown problem for many people. Please, questions? I start here in the front.
Yeah, Subsidence in Mexico City is amazing. So one GPS station in international airport recorded 26 centimeters per year. It's like 1 foot per year. So now, I want to know that do you did any research on the lateral subsidence? So what is the rate of lateral subsidence? Lateral subsidence means that without groundwater pumping, because of gravity, that sediments will also do the consolidation. So what is the rate of lateral subsidence?
No, without pumping, we have any sediment.
Sediment
is due to the pumping. Maybe some part is due to the weight of the buildings, but that would be really secondary.
It should be at several millimeters per year, or sometimes can go to almost 1 centimeter per year in some area. So if you talk about 1 century scale, that still can be somehow can still be considerable.
Our models are based only on pumping systems affecting the distribution of pore pressure and using the increases in the effective stresses. And next question.
Okay, next question. You mentioned obviously you study pore pressure evolution in the clay, and you also say there are wells there. But what are the special methods you use, because the wells will subside as well? Are they referenced level? No, I mean the level you measure in wells. You measure water levels in the well, but the well itself is also moving. So how often are the elevations of the wells recalculated to get proper hydraulic head?
It was not built finally due to political reasons, but for this special work, we made some measurement of pore pressure, and of course, the change of position of piezometer was taken into account, because that's significant, yes.